Here we are again. Welcome to Chapter 6, Chemical Reactivity and Mechanisms. Now, enthalpy, we should briefly remember from general chemistry. Whether that was the first semester or the second semester, we've talked before about delta H. Enthalpy is the heat exchanged in the reaction and its surroundings, between a system and its surroundings. Specifically, what we are going to be using delta H for. You might have done it in calorimetry. You might have talked about it with Hess's law. What we are going to be able to use is the idea of delta H as it relates to bonds breaking and bonds formed. So you might have seen this equation before where you have the delta H and it says the bonds broken minus the bonds formed. These are looking at bond dissociation energies. And what a bond dissociation energy is the amount of energy required to break a bond. Remember that bonds are formed because of attraction between a electron and the nuclei. And in order for us to break a bond, we actually have to put energy in to the bond. We have to pull it apart. And in order to do that, it requires energy. So these are all the required energies to break a bond. Why we have that subtraction right here is because we can use the bond dissociation energies, just the opposite sign, in order to say that's how much energy is released to form a bond. When we form a bond, energy is released, and it's the same amount of energy that's required to break it, just the opposite sign. Bond dissociation energies are always endothermic. And so in order to form a bond, we would see an exothermic reaction, just the flip of the sign, right? The other reason why we want to think about this is we do know that when we take two atomic orbitals, let's just say these are 1s orbitals for hydrogen. When we take those orbitals, one hydrogen and one hydrogen, when those two atomic orbitals come together, they lower their energy to form a bonding MO. Definitely lower in energy. There is the higher in energy sigma star that it remains empty, which is why H2 is a favorable diatomic molecule. The electrons must overcome and absorb energy in order to separate these two electrons. So these two electrons right here in the bonding molecular orbital, that's what we're talking about. The energy required to separate those two, remember, would have to go backwards. Higher energy, this is an energy diagram where energy is increasing on the y-axis. And so in order to actually separate those two electrons, you're putting them back into their atomic orbitals, and that is the amount of kinetic energy required to overcome the stability of that bond. Bonds can break in two different ways. The first one that we can see most often is called a heterolytic bond breakage. So bonds break heterolytically, where if we had bond X, Y, where we form a double-headed arrow, and the bond becomes a lone pair. So two electrons moving at once, and the bond will become a lone pair on one specific element of that bond or one specific atom. What this makes is ions. We saw a heterolytic bond cleavage in acid-base reactions. And so with these ions that are forming, we are breaking the bond with 2 electrons moving at a time. This is the most often one that we see in this semester, but there is going to be another way that we can break bonds, and we'll briefly see it in this semester, but we'll talk about it even more next semester, and that's called homolytic bond cleavage. With a homolytic bond cleavage, when a bond breaks homolytically, what we start to see is that one electron is going to move at a time. Notice that that arrow looks different. This is called a fish hook arrow, single-headed or fish hook arrow. And the reason why those are different is because there's one electron moving at a time. And so what we get out of these is not ions, but a separation of the bond evenly, and we get what we call radicals. Now, radicals are neutral atoms, but they do not have an octet. And so when we see these arrows, one electron is moving at a time. So we see twice as many arrows, right? We see 2 arrows for that bond homolytically cleaving, homolytically breaking. Bond dissociation energy is corresponding technically to the amount of energy required to homolytically break the bond, but we can utilize it in heterolytic reactions as well. With entropy, a bad definition is the amount of disorder. I'm not going to write that down. That's not a true definition. It can be describing the molecular disorder or randomness, but what we really want to say is that entropy is the number of vibrational, rotational, and translational states of energy of a compound. And really how it is distributed, how these translational, vibrational, and rotational energies and states, how are they distributed throughout the molecule? So what I really want us to consider here is this idea that we saw entropy a little bit in general chemistry as things in gases. Why do gases expand to spread out over a given area? Why don't they just clump up into one side of a container? But the more space, the more freedom that the molecules have to spread out means more entropy. And so that is favorable, right? What is favorable for us means what should happen. And what is favorable for us is an increase in the system entropy. We related this to a positive delta S, right? If delta S for the system is positive, this is what we called increasing entropy. And that was favorable. If delta S of the system is negative, we said that was decreasing entropy, more structure, less disorder. You can think about that as more order, right? And that was not favorable. So when we're looking at entropy, it is one thing that I definitely want to say, how can we qualitatively look at entropy? And that's the key. It's going to be a qualitative look at entropy. We won't have numbers associated with it. I know we did in general chemistry, or a lot of times we do, like delta S's of formation and delta S's of certain bonds. But what we really want to think about is there are two main factors that will affect delta S of the system. So for our qualitative look, what we want to first think about is when there are more molecules, or we can think about moles, right? More moles or more molecules of product, delta S of the system is positive. What this looks like is if we had one molecule going into two. Molecule AB now becomes A and B. There's one molecule and we're making two molecules. You can look at the coefficients of a balanced equation. I'm pretty sure we did that too in general chemistry. If not, no big deal. We now know. And the second factor that we can look at, this one you probably haven't seen, when a cyclic compound becomes acyclic, the delta S of the system is positive. So think about this molecule becoming this molecule. Now, we do know for a cyclic molecule, there is limited rotation. Think of chair cyclohexane. It does rotate, but not a full 360 degrees like a Newman projection did for a alkane. We do know that pi bonds have a limited rotation, right? So that can also be something like this. But typically what our best two things to look at is the number of molecules, comparing the reactants to the products, and limited rotation to full rotation for reactants and products. All right, is delta G. Gibbs free energy. So a negative value for delta G means that the reaction is spontaneous. A positive value for delta G means that the reaction is non-spontaneous. And so enthalpy is important and entropy is important. So we're looking at the overall idea as being, well, if we can look at entropy and decide, and look at enthalpy and decide, is it favorable or not, then we can understand if the reaction itself is favorable. Is an equilibrium constant, right? Products divided by reactants. And that is what we can use to show the degree to which a reaction favors the products or the reactants. If the KEQ is greater than 1, products are favored. If the reaction KEQ is less than 1, the reactants are favored. And then if the KEQ is equal to 1, neither are favored. Reactants and products are equal in concentration. So KEQ, delta G, delta H, and delta S are all thermodynamic terms. It only describes the relative stability of the products and the reactants, but not how fast or how slow they go, right? And we can use KEQ to find delta G as well. The negative RT, R being the gas law constant, different units, temperature being in Kelvin, and the ln, the natural log of KEQ, will give us the actual delta G. It's what we've been talking about, right? If we see a reaction coordinate with the reaction progress on the x-axis and some sort of energy on the y, right? When we start putting in the lines, right, all we know is reactants and products. Here is thermodynamics, right? Kinetics is what you get in the middle. This is kinetics. And it's together with thermodynamics and kinetics that we can truly understand everything that is happening in a reaction. So just because a delta G is negative doesn't mean that the reaction is going to happen fast or slow. All that means is if delta G is negative, it's going to happen on its own. It's spontaneous. So it could be something like a combustion reaction, which is very, very fast, very exothermic, very, very exergonic, happens very fast. Or it could be something like diamonds going to graphite. Everybody's diamond ring is going to eventually turn into a pencil. But it takes millions and millions of years for that spontaneous reaction to take place. So what does that mean for us? Thermodynamics is not the only piece of our puzzle. We also need to understand kinetics. And so the rate of the reaction, how fast or how slow, how many molecules are colliding at a given time period, are all very important. Now we are going to deal with 5 things that affect the rate of the reaction. We might have seen some of these, but we're going to be able to see a lot more and see a holistic picture once we get into reactions in chapter 7. All right, so again, overall, what did we just learn here? Or what did we just remember? There are a couple things when looking at a reaction coordinate diagram. Reactants to products. That's thermodynamics. The pathway at which those happen, where we get a transition state, where we get an activation energy, that's kinetics. Thermodynamics tells you the stability of the reactants and the products. Kinetics tells you how fast a reaction will go. They are completely different concepts. However, together, they are an extremely powerful tool to understand how long are you going to be in the lab? Is that a good way to mass produce a molecule that's a drug? Is that an option for a biological system to respond? Is whatever we're looking at, thermodynamics and kinetics is a holistic view of understanding a reaction. So we're going to look at these reaction coordinate diagrams a lot in class, but what I would say is let's make sure that we can read them a little bit better. Multiple steps, right? When we see a bunch of squiggly lines, reactants are always at the beginning, products are always at the end. When we start thinking about the kinetics, what happens in between? I'm going to label this as step 1. That first hill is going to be a transition state. I'm going to say transition state 1. It will have an activation energy, EA1. What's important to note is that does not need to result in a product. It results in an intermediate if there's a second step. This is step 2. Transition state 2. Activation energy 2. Right? Between two steps are what we call intermediates. They're molecules that are able to be isolated, right? But they are not the final product. So an intermediate is the species formed during the course of the reaction. They are an energy minima, right? There's a little valley there at the intermediate. And they are observable. They're actual species, and you can exclude them. You can pull them out. You can identify them, but they usually aren't the final product. The transition states are the hilltops in between those for those two steps. The two hilltops, they're maximas, right? They're energy maximas. They're the energy required to get over the hill, to proceed the reaction. Transition states are not isolated molecules. They're the in-betweeny. They're the positions where we can't actually see them in real life when bonds are breaking and bonds are forming. So when we draw a transition state, we'll see that they're going to be not real molecules, just more like theoretical points when the bonds break and form. We'll call this step 3, this final step. It also has an activation energy, right? And it comes from an intermediate and goes to a product. So there are 2 intermediates here, 3 steps or 3 transition states, reactants, and products. What we are going to be able to do is look at a reaction coordinate diagram for specific reactions and be able to identify an intermediate or a product or a transition